Okay, hello everyone. I'm Antigona Pajaziti. I'm going to talk about the topic that we were working this 2 weeks. So we were wondering if a genus 5 curve over F47 with 113 rational points exists. So first, let me give you that a genus 5 curve can be of 3 types. A genus 5 curve can be either hyperelliptic, trigonal, or a complete intersection of 3 quadrics. What do we mean by hyperelliptic? We say that a curve is hyperelliptic if there exists a morphism from the curve C to the projective space P1 of degree 2. In this case, we can present our curve with the equation y squared equal to f of x, where the degree of f is equal to 12 or 11. We say that a curve is trigonal if there exists a morphism between from the curve C to the projective space P1 of degree 3, and such a curve can be represented as a plane quintic with a node or a cusp. And finally, we say that a curve is a complete intersection of 3 quadrics in P4 if it is not hyperelliptic and it is not trigonal. Okay, so we recalled the last result that we talked about last week. So we find out all the possible orders of the automorphism groups of the curve X. And all of these automorphisms are defined over the finite field with 47 elements. Now we use this information and we try to see if we can eliminate some possibilities, and what can we say more using this result. So first, you might ask, why 47? Is this number unique? Does it work only for that finite field? Before we talk about that, let me give you the definition of an optimal curve. So we say that a curve C of genus G over a finite field is called an optimal curve if its number of rational points attains the upper or lower Hesse-Weyl-Serre bound. And in our case, 113 rational points is the upper bound. So the curve that we mentioned at the beginning is the optimal curve. But F47, it is not unique because all of our methods, they will work for an optimal curve of genus 5 over a finite field for all primes Q that satisfies these 2 conditions. So Q, it's not congruent to 0 or 1 modulo 5, and also the integer part of 2 square root of Q squared minus 4Q is equal to minus 19. So from now on, I will take the general case FQ. Okay, so now let X be an optimal curve of genus 5 over FQ, which satisfies this equality. Zaitsev in 2015, he said that such optimal curve of genus 5 is not hyperelliptic curve. So now we managed to eliminate the first case of the genus 5 curve. And also we have the result that if an optimal curve of genus 5 that satisfies that equality over finite fields FQ exists, then 5 divides the order of the automorphism group of this curve. So now we eliminated the hyperelliptic curve, the hyperelliptic case, so we see how we can use this information to talk about the trigonal curve case. We first recall that a trigonal curve, we say that a curve is trigonal if there exists a morphism 5 from the curve X to P1 of degree 3, and we define by, we write by D the pre-image of a point P in projective space P1, and we call this, this is a divisor of degree 3. Then the image of this map here under the divisor kappa minus D inside P2 is a curve of degree 5 with a singular point. So, and moreover, this divisor D is unique up to linear equivalence, and the uniqueness of such divisor, it follows from base point 3 pencil trick and Clifford's theorem on divisors. Okay, so why do we need this? We know that if such curve exists, then 5 divides the order of the automorphism group. So let's see what is this automorphism group of this curve in the trigonal case. We conclude that all automorphisms of this plane singular model of a trigonal curve of genus 5, they are linear. So if we take alpha to be an automorphism of X, then by the uniqueness of D in the previous slide, it follows that the divisor, so kappa minus D and alpha star of kappa minus D, they are linearly equivalent. But this exactly means that alpha star is a linear automorphism of the linear system associated to kappa minus D. That is the set of all divisors, effective divisors, which are linearly equivalent to kappa minus D. So then this means that alpha is a linear automorphism of our curve here, which was inside P2 of the image, of the image of X, and therefore all automorphisms of X are linear. Okay, so now we have the map of phi kappa minus D from our curve X to P2, and we also know that the automorphism of the trigonal curve of genus 5 are all linear. So this means that the automorphism group of the curve X is a subgroup of PGL3 FQ. So PGL3 over FQ comes from the projective space P2. Okay, so remember the two conditions that we gave for the prime Q at the beginning. So we said that Q is not congruent to 0 or 1 modulo 5. And also, we had that the integer part of 2 square root of Q squared minus 4Q is equal to minus 19. Now, from those conditions, it follows that 5 cannot divide the order of this group. And now we have a contradiction, because the theorem of Zaitsev said that if such curve exists, then 5 must divide the order of the automorphism group. So we conclude that there is no trigonal curve of genus 5 such that 5 would divide the order of the automorphism group. So until now, we managed to eliminate the hyperelliptic case, and we eliminated the trigonal curve case. So what we are left is complete intersection. Okay, so what was a complete intersection? We say that okay, so let Q1, Q2, and Q3 be quadrics in P4. So by complete intersection, we mean that we can represent our curve X by these three quadrics inside the P4. Here as well, because the information that we know is about the automorphism group, so we let alpha be the subgroup, alpha generate the subgroup inside, which lies inside the automorphism group of X, which is isomorphic to Z quotient 5Z. And here we are in PGL 5 over FQ, because we are in the projective space P of dimension 4. Okay, now this alpha inside PGL5 can be represented by a matrix, and we name it by M. So inside PGL5, M to the power of 5, it is equal to some lambda times the identity matrix. So if we do some calculation, we know that there exists a nu inside the multiplicative group of FQ, such that this nu to the power of 5, it is equal to lambda. This has a solution inside this group, because we had the condition that Q is not congruent to 1 modulo 5. And we can write M as nu times M prime. Then it follows that the fifth power of M prime is equal to identity matrix. So we can assume that the characteristic polynomial of the matrix M, it is equal to T to the 5 minus 1. And we are working in FQ. Okay, so this is the characteristic polynomial of the matrix M, and it's also the minimum. At the same time, it's also the minimal polynomial of the matrix M. So this gives us that the matrix M is similar to its companion matrix, which is this one, and at the same time, this is a permutation matrix. What do we mean by that? We have transformations that send x to y, y to z, z to u, u to v, and v to x. And these were the variables that we used to present our quadrics. Okay, and also, so now we had alpha, an element of this subgroup inside automorphism of X, and that alpha induces a linear automorphism, which we call it alpha tilde, alpha tilde is an element of the automorphism of the vector space, which is generated by the quadrics Q1, Q2, Q3. These quadrics are also linearly independent in P4. Now, we know that this alpha tilde cannot be of order 5, because 5 does not, because of the condition that Q was not congruent to 1 modulo 5. Sorry, the two conditions that we had on the prime Q. So the only case left would be for alpha tilde to be identity. What does this mean? It means that it acts trivial on the quadrics. So alpha tilde of Qi is equal to Qi for any I being 1, 2, or 3. Also, we can represent our quadric with the matrix, all the monomials in this way. So we have 3 different colors here. So because alpha tilde is acting trivial on the quadrics, and also we have, so this transformation x to y to z, and so on, then the coefficients of x squared, y squared, up to v squared, they have the same, they are the same. Similarly, xy, yz, zu, uv, and xv, and also the one in the green color. If we name all of these by P1, P2, and P3, now we had that Q1, the quadrics Q1, Q2, and Q3, they were linearly independent. We also see that P1, P2, and P3, they are linearly independent inside P4. So we can take Q1 to be equal to P1, Q2 equal to P2, Q3 equal to P3. And so we can say that, okay, if such curve exists, then we can represent it by this polynomial, so P1, P2, P3 inside P4. But, so we want our curve to be a smooth curve. And in this case, if such curve would exist, as you can see, it would be unique. But when we check this curve, this is not a smooth curve, so it fails our property to be a smooth curve. So we conclude that there exists no optimal curve of genus 5 for the complete intersection case, such that, again, 5 would divide the order of the automorphism group of the curve. So we eliminated the hyperelliptic case, we eliminated the trigonal curve case, and the last case of complete intersection. So what can we conclude from all of this is that there is no optimal curve of genus 5 over the finite field FQ, where Q is not congruent to 0, 1 modulo 5, and the integer part of 2 square root of Q squared minus 4Q, it is equal to minus 19. So this is what we concluded, and of course that it would be like nice question or future work, I'd say it, if somebody would be interested to check what would happen if Q would be congruent to 1 modulo 5. Thank you.